experiment is not like European, it is international. You will find most of the countries are contributing their knowledge for this discovery. So this is not just for one person, it's called together we can get also knowledge. So I'll just tell you, starting from my talk actually, what I'm going to tell you actually past. Before Higgs boson where we were, when we observe what happens, is it the end of the world that we find? Or what is going, is it true that you have done everything, nothing for us? So there are many things are there to do, and it needs more than even Einstein, more than the Higgs to make us successful. We need more than Peter Higgs also. If you the generation who are coming, they have the potential to beat. Otherwise, we are so challenge is bigger for young. Don't think that there is nothing for you. So let me start my talk. Okay. To tell you about the particle physics, where we start such medical science, COVID tika. Everybody say, okay, we got it something. But in particle physics, what do we get actually? Why it is not very popular? Because it does not give you direct. We always think about where do we come from. People think about after I death, but we are thinking about where we come from beginning actually, not my grandfather. I'm thinking about grandfather, when grandfather was not there also. So it goes slightly bigger in picture, which common person may not understand. That why do I have to care about if I'm not worried about my grandfather's grandfather? I don't care, but we care. So that is where our area of research goes. If I talk to someone, he may disconnected with me saying that, well, okay, I'm only worried about my grandfather and grandfather, maybe grandfather, maybe 100 years, maybe 200. Beyond that, I am not interested how it is going to help me actually. It is not helping us. It does help us. How? I will explain also. Then how the Peter Higgs discovery of this particle, which is what, because it is the most critical particle which governs us. Okay. So where does come into fit in the particle physics? Why we give so much credit to Professor Peter Higgs? To do that, I will point actually how this Large Hadron Collider and the detector plays a bigger role to discovery actually. That is the beauty of this theory actually. Then we'll discuss what next actually. Just in short for fundamental particle. What is fundamental particle? You might have studied in your college or fundamental particles is, if you look at the time scale, I'm not going beyond 1900 also. When I talk about early 90s, that's my T0. My fundamental particle was atom. Everybody is happy. As we move about 1910, we said, no, 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 atom is not, it's nucleus. See, you go to 1940, you get into the structure of nucleus, which is proton and neutron. You further go into the 70s, you say, no, proton is not fundamental, it is made of another particle called quark. So this is a fundamental particle, which is the smallest building block of our visible matter. Everybody here is made of proton. but every proton is made of quark. That means we are same. Me and the computer are same. If I go to the level, it's the same. So I have a life, computer has a life. And computer is talking to me because he's made, I am also made of quark. How we are connected? We are same. So we have to go to the very root level, find out that how we are connected, not the top level, how we are different. Then at this point, we are not stopping. We are still going on to the Large Hadron Collider. We think quark may not be the fundamental particle. Maybe quark has a structure. Now the question is, why it happened in 19th century? Why not 18th century? Why this was not done in AD 500, maybe BC? You go, why it is not done? Maybe we are lucky, maybe. So main fundamental thing is, if you want to measure something, what do you want to know? Let's say I want to measure the length of a building. I need a tape. If you look at the tape, there is a small division is there. That is called least count. That is the minimum length you can measure, isn't true? Now, if you want to more accurate, you get a digital meter, right? Nowadays, people use a laser and do this, and they give more accurate. That means we got to know the instrument which can measure the length scale of this. And that technology was not there before 19th century. That means it's a technological breakthrough allows us to probe the length scale of 10 to the power minus 16 centimeter. So maybe 19th century people got more smarter too. Technological revolution has started actually. Technology does help us to bring the science deeper. So technology and sciences are not different. They are in the same roof. Then only you can get the success. Let me tell you how. When you measure the size, how is it related to energy? Now, I am not talking about this scale. If you go below certain length, you cannot measure using a scale. So you have to use the energy. So how you use energy to measure the length? This is a new technique actually that is particle physicists use. If you talk about this to a general person, no, I don't care about that. Okay. If you talk below this length, I have no business there actually. Okay, because it doesn't help me actually, right? So how, first thing is, let's see, in order to see an object of size r, if r is the radius of the object, what happens actually, one must use the light with a wavelength should be less than radius of that set. Okay, now if you use visible light, then you can see the bacteria. That's fine. So what instrument you use decides what the size of the object you can see. So that is good enough for us, visible light, and we don't need any technology. And I can convert that to energy also. So this visible light comes from the atomic transition, and that energy is around an electron volt. Okay. Now, if I change the energy, how I go? Now, if I want to resolve the virus, I have to use electron microscope. That energy is kilo electron energy. You see? So length and energy is now correlated. So that is how we particle physics want to prove the fundamental building block of this universe. And if we talk about proton size, you need a GeV range, giga electron volt energetic particle to probe the size. And if I go further, which is 10 to the power minus 4 for me, pretty small actually, then I use TeV scale, tera electron volt energetic particle. how do I generate this particle, energetic particle? I don't know. Then electromagnetic theory tells you how to accelerate the particle. That is where I take help of my physics. And that is where accelerator comes into picture in particle physics. So we can build accelerator which can make the higher energetic particle. I'll tell you how we do. It's very simple. You know how to accelerate a particle. You can do the electric field kick. You can energize the particle, right? No, everybody do. So I'm going to discuss that actually. Let's go back actually. What is this fundamental building blocks? So if you look at the fundamental building blocks, I'm just telling you this cartoon, you can see there are six particles, but I put in three. If I look at my Earth, it's me, is mostly made of first generation of quarks, which is UD quark, which is made of proton and neutron. If I want to atom, then you pick up the electron, it become atom. That is what you see the Earth. All visible matter in this universe is just made of first generation. But from the research, we found that there are not first generation, there are three generation of lepton exist. Why it is there, we don't know. It is explainable by this, but these are we can create inside the lab. Fundamentals for research you do. Some of the particle you may know, muon. Cosmic ray produce muon, you might know. That nature produces image. We can detect the particle in our lab also. We don't have to create. But some of the particle we do have to create. Now, if I look at this actually, how these fundamental particles interact. How do they talk to each other? So first thing is, electromagnetic. If the particle has charge, it will be electric field. So they can electromagnetic, they can electron proton. So this is one theory, which you know the equations, you study electromagnetic theory. If you look at the nucleus, it's a strong electromagnetic, the deep pressure. If you look at the sun, which gives you the light and heat, it's a weak. Then these three forces together can be explained by standard model of particle physics. The standard model which we are proud of, the three can be explained. But still, when these three were explained, if I talk about standard model is a nice bridge or Manson, you can see the Higgs particle is here, which was missing. If you see a beautiful thing, you can say there should be something is not broken, but we did not find this Higgs particle. That was the missing building block for a beautiful theory. Everything is understood. And these interactions are explained through the exchange of particles called mediator boson. In case of electromagnetic, you have photon, which exchange between electron and proton, electron and electron. Whereas strong, you have a gluon. Gluon means glue, is stick together. Gluons, and W and G, which is a heavier boson, is a weak. Then altogether, you have also gravity. But in standard model, still has no answer for gravity. That is open question for us. How do we incorporate gravity into the standard model? That is not yet done. Okay. Now, with this actually, we were here without Higgs. Though theoretically, if we put Higgs, then everything is understood. That is where we were curious whether that's 1964. And we discovered Feynman give a very nice cartoon, means interaction among the particle. You can put a called Feynman diagram, and you can easily calculate what would be the probability of producing this process. Nicely in a piece of paper. And if you are interested, you can look at the Feynman lecture. See all the very nicely matching. Measurements are from the experiment. Okay. This gives just a cartoon to calculate. How a cartoon can tell us what production I have. That means we know profound theory behind this actually. This is how accurately we know. We can tell you find actually. So this is being tested since 1960s. Every time we go, we find exactly matching. Okay. So when this theory were given, even 6 quarks were not discovered. But they told there were 6, and they also told what the mass. And you just do the experiment, you find the mass is matching. As if he is the astrologer. You can say that he does everything as accurately predict, he knows what the universe is governed by. So we are so much fond of this theory because you just put and it gives you what you expected. But the question is, why it is so difficult to find Higgs actually? Why this Peter Higgs started to give this theory? Why Peter Higgs was curious that why we should need some modification? The problem is you have theory which is SU3, SU2, SU1, which is the 3 different interaction I told you: electromagnetic, weak, and together is one line. You can write the Lagrangian. It's okay, I understood everything. But the problem is, before Peter Higgs gives this thing, this describes how fundamental particles interact by strong, weak, and electromagnetic force. That's fine, quantum field theory. It describes interaction of particles with force carrier. That is also fine, very good. Where the Peter Higgs comes into picture then? Only consistent with a Higgs boson, something like it, because if you do this, that means you need this. Otherwise, this is a problem. Problem is here. Photon is massless, you know that, right? Gluon is massless. It's just, but W and G are massive. That is where symmetry is broken. Why a carrier who is supposed to be massless, all of a sudden W and G is massive? And the same theory could not explain the carrier can be massless and massive. That was the problem in the theory. And that is where Peter Higgs comes into picture and gives the modification which gives the photon massless, W and G massive, without breaking theory. He didn't give a new theory. So that's the beauty. Beauty is just add something, keeping photon massless, W and G massive. Then everybody is happy. And with this, you can do everything. No. Higgs massless, because W and G is supposed to be massless because the force carrier. If you put this Higgs mechanism Who decides that it increases at some point when it goes to 90 GeV? G boson says, okay, my mass is this, I will not increase. Who decides this? This is where the Higgs mechanism does. When it reaches 90 GeV, Higgs says beyond that it cannot go because this is the mass of it. Now, caution to apology to the experimentalist for having no idea mass of Higgs boson. The Higgs mechanism never told what is the mass of Higgs. Now Higgs mass can be EV to TeV. Now I should have an accelerator who can go EV to TeV. We cannot design that. To get a TeV, multi-TeV, I need a accelerator, high tech, and technology not there. That is why even 75, the theorists already told it is not a mistake of experimentalists. It's our mistake. We don't tell what is the mass of Higgs. It is the biggest question for experimentalists to find us where it is. And this is the biggest challenge for experimentalists. So many experiments can go to the garbage without discovery also, because we don't know. So that means we go to all territory to find. And when you know you don't know, you should be very careful you are not missing your signal. If you miss, it's done. So experimental's job was very challenging. You have to find something which you don't know where it exists. Now, unlike the case with the charm quark was told what is the mass, people found it's not a, but Nobel Prize was given to experimentalists discovering the charm quark. You see, even theory told for not being this sure it's coupling to the other. For these reasons, we do not want to encourage big experimental searches for Higgs boson. Even experimental want to propose multi-billion-dollar proposal, theorists will say, okay, I don't think we should spend that much money now, okay? Shut off your experiment, because we don't think so. We are not ready to spend money because it's not so important at this point. But we do feel that people performing experiments vulnerable to the Higgs boson should know how it may turn out. So they're saying that experimenters will know actually anytime it can turn out. So basically, theorist giving a theory, sitting quietly, and maja le rahe ho, you enjoy, let the experimenter do the dance and go and find. It took so many years. It's not easy to find. Okay? Now, same people waited, and it went to how long you can wait. By mid-90s, same people were impatient. We cannot wait more, let's spend money. That is where LSE comes, so that we need Higgs. Whole world says we need Higgs. If it is billion-dollar, multi-billion, we don't care. Without that, there is no future for us. That is where all the money comes into picture, all resources comes into picture, making the most amazing technological breakthrough, detector and accelerator, it comes because it is the need of everybody, not for us. That is how the Large Hadron Collider and CMS ATLAS experiments come into picture. Though it is a pretty big, not a single country could afford. If you look at before, usually a single country can afford. If you go to Formula, it is mostly US. If you go to Japan, it's a KK. They have money. But when it comes to Large Hadron Collider, even European Union also could not afford. They said, no, we don't have money. So everybody should pay. So every country, even India, is also paying their share. And we are part of the team. we contribute to the discovery. How do we find then? If people say, okay, you go find, do you really rely on only particle physics accelerator? No. So we can search many different ways, and I will tell you how it is. Now, one way is recreate the condition which existed about 10 to the power minus 12 seconds after the Big Bang. That is where Higgs was there. Field was there. That is where the mass comes, because Higgs gives the mass. Now I have to go back in time. Think about, now we are sitting here more than 10 billion years after the Big Bang. Now, if I ask you what happened when our universe was 10 to the power minus 12, 13, 14 seconds, can you tell us? We say, oh, I am not belongs to this universe. I belongs to my father. I can only tell my birthday. That's it. Beyond that, you are not belongs to this universe. Who cares about the universe actually? I care about my family. And my birthday, I can tell. Even my birthday also, I cannot tell you also 10 to the minus 12 seconds. Can you tell? No, it doesn't matter to me actually. Why? Because when you are 1 minute, all the organ, everything, after that, once you come to this world, you just grow. Nothing changes. Right? If you look at this cartoon, this is T0 when the Big Bang happens. And this is where the expansion, which is called gravity, becomes weak. Inflation. So fast it expands and it stabilizes. If you come here 3 minutes after the Big Bang, so already your nucleus is already formed. After a minute of Big Bang, 10 billion years, nothing has changed. Nothing has changed. We just grown together, making galaxy, all these things. Physics is same. What happens in 1 minute decides your 10 billion years. So when you are giving birth, 1 second decides what happens your lifetime. But that 1 second we ignore, saying that my clock was not digital, is analog. So 1 minute is the least count. So I wrote my son's birthday, time, and minute. I lose that 1 minute, what happens? Where, as a particle physicist, we think below 1 minute is the interesting thing to know. Okay. So we have to go here. How do we go there? How do we go? We cannot have a time machine, give the time. So what we can do actually, we can recreate the condition which were existed at the time when universe was 10 to the minus 12 seconds. What is the condition? At that time, I was not there. What was there? What was there? Temperature, volume, nothing else. Energy. So everybody were energy. Me was energy also. Can you do that? Yes, we can do that. We have a machine which can create that condition. If that condition exists, if I create in a lab, if Higgs was there, Higgs will be produced. So that is the way we have gone actually. Now, second one is, we don't discourage any other physicist or branch to see. There are people who work like Hubble telescope. They are also curious to know how we have evolved. But Hubble telescope it can go about 2 billion years after the Big Bang. So Hubble telescope tells you within 2 billion years how we have evolved. Okay, that's also interesting. People do. And if you go further, called double map experiment, it gives you 300,000 years after the Big Bang. That's the most way you can go. If I look at the 3 ways, only my Large Hadron Collider takes me back the time Higgs was there. That is why people put the money more there actually. Let's go there. This motivates us to do this experiment. How to find Higgs? If I go there, then I need a machine. That is why LSE is called time machine. It brings It takes me to the back in time. So I need an accelerator, which is called Large Hadron Collider, which will take me to that instant of time I need. Not only that, once it produces that condition, if Higgs was there, Higgs will be produced. Now I need detector. ATLAS and CMS, two general purpose detector, were made to detect Higgs. Now we have to build the detector. Not only that, we need the theory always to back yours. That okay, when we find theory should say, yeah, it looks like a Higgs or not, actually. They should tell us. So this is on track. If you look at here, you have one accelerator, Large Hadron Collider. You have two detector. Why? Why you have two detector? Who can tell me? Very fine. But we always say one child is good enough. Right? At a physicist, we don't believe in one child policy. At least two. So when we discover, two people have to independently verify. That is why two. If we want to build another accelerator, we can do this. That will cost another $10 billion. We want to do that. We don't have money also. Just for a verification. But we thought we can have two experiments, different location, but same accelerator can give the collision. Let's go back. If you look at the particle discoveries, I told you, we are made of only first generation of fundamental particles for the UQ, D, and electron. But if you look at the discovery, we have discovered so many particles which are existed, but their lifetime is very small. They decay, and we can detector can decay and do. And also I put it here, Higgs is discovered here. So we are talking about pre-Higgs discovery now. Okay, Higgs was not there. So you can see actually always there is a discovery going on. At least we know how to create the particle inside the lab. Okay, let's move actually how we are going to discover. Now you are in a mission to discover, and it is true for anybody actually. When you go for a discovery, you have to do all the preparation, what is the consequence, everything you have to plan. Large Hadron Collider, I'll go with not required, but at least I can glance you. This is the Large Hadron Collider ring, 27 kilometer of circumference. And you have a CMS experiment is here. ATLAS is here. Almost opposite. Then you have two more experiments called LSCB and ALICE. It does this CP violation, which is another profound mechanism. And ALICE is probing the when the universe is cooling down, before it becomes quark and gluon together to make proton, there should be a transition where quark and gluon should be free. And they are trying to understand whether quark and gluons are free or not. Okay. There is a state of matter where quark and gluon should be free, not bound. Okay. That means strong interaction was not even strong enough to bound together. And this is CMS and ATLAS. So ATLAS I worked before coming to IIT Madras. Now I am part of CMS because India is part of CMS. So I have to switch my loyalty. I have to work for the country. So I am working here. Okay. So sometimes your loyalty also doesn't stay with, you have to loyal to people who you work actually. This is simple. I mean, you can forget and we relax a bit that we'll talk about very basic physics actually, not big physics always, okay? What do we do? Everybody knows E is equal to MC square, right? Yes? Okay. We do also need this because mass and energy same. That is how we can create a new particle with different mass if we have energy. So energy can be converted to mass. So if two proton with energy 4 or whatever TeV, you will have total energy available in total, you just add. If a particle mass is less than this, there is a probability that particle will be produced. That's the basic fundamental science. There is no bias. It's not like it's my country, your country. It says if your energy is this, you can produce this. And that's the probability a theory can calculate. How often you can create the particle. And you can measure it. So in case of proton is made of quark and gluons. So when a proton-proton collision happens, basically collision happens between quark and gluons actually. Now you think about proton takes 1 TeV, but it has 3 quarks. They will share the energy. So energy available to make a particle is really less than the total energy of the 2 proton, right? So that is why even if you say 13 TeV, we may not get 13 TeV as energy to produce a 13 TeV particle because of 3 quarks are sitting there. Another proton has 3 quarks, and there are a lot of gluons. They can carry on energy. So basically, you have less energy available. That is why proton-proton collision is not suitable for doing very precise physics because of reason that we don't know how much energy is available. It can fluctuate. So we know Einstein told us, so no problem, but Einstein never to ask us where the mass come from. You see, he used mass to get the energy mass. Everybody is happy, whole world is clapping. Nobody asked, what is this mass? Because mass concept was not there. People thought we know how to mass, created a mass in theory. They can do the correction, make the mass until the symmetry is broken in the gauge boson. That is where nobody could answer. That is where they are in the wrong side that, okay, what we are thinking we can generate the mass in the theory, it is not possible. This is not working. Okay. The accelerator comes pretty early in the 1940. That is why technology, what I told you, is accelerator. And it started in 1940. That is how most of the particles started discovered, because we started using the accelerator to create the large energy. And just to getting 80 keV accelerator, Professor Lawrence got the Nobel Prize because it's a technological breakthrough. You can do circulars. Okay. After that, we never stopped. We are creating bigger and bigger accelerator. It's going to 27 kilometers. Now, in future, we are going to 50 kilometers, 100 kilometers. Sometimes we are thinking we can do the Earth. We need more energy. Why? Because to probe shorter the distance, more the energy. If you want to know what happened to this universe 10 to the minus 42 seconds, where gravity was strong, then we might need a accelerator of this. Not Earth will not be enough. That is why we are thinking understanding of gravity is beyond our reach. We may not be able to create the condition when gravity was strong enough to understand. So this is a big challenge for new generation to find different way to accelerate. That is why laser technology comes into picture. We cannot do this electricity. So challenge for you, if you can do the accelerator, which can give you to 100 TeV, 500 TeV with 1 kilometer of ring, no problem. That requires very smart way of thinking how we can do that. Okay, so there are a lot of challenges are there to go, but last 100 years, maybe 8 years, is easy for us actually. Still, we think it's a tough, and tougher thing is coming for new generation. This is what people use actually. This is Maxwell's equation, Newton's equation. You can figure out, and if you know the E, you can get it. This is very simple. Okay, so it is not very difficult, and electronic theory is well understood now. Because of that, we have everything is electronic if we are using nowadays. Then you need the magnetic field to keep bending the track. So you need electric field as well as the magnet. More the energetic particle, you need a more energetic magnet also to bend. Okay. So this is also known to us. It's not new. And Large Hadron Collider is the tunnel. This is the ring. Inside it, the 2 tubes are there, and 2 protons are going opposite direction. And this is the dipole magnet going to the under the ground. So accelerator is underground. It's in 2007. People are so excited that LSE will definitely discover something. Okay. Now, the Large Hadron Collider is 80 million times what cyclotron was built in 1940. That cyclotron got Nobel Prize, but LSE did not get Nobel Prize. You see, by expanding yourself, you don't discover the technology. You just use same technology. So LSE, you see, 80 million that people say, wow, you can, no Nobel Prize. Okay, the first person got the Nobel Prize. It now it is more than that. In 2007, it was already $8 billion spent. Okay, it took more than 15 years to conceive all the technology. You have 8.4 Tesla dipole magnet. You have 30,000 ton. Then it cooled to 1.9 Kelvin. And most of the liquid helium in the world is sitting in the tunnel. We are using that for cooling. Okay. And since it's in Switzerland, we always love to connect to Swiss chocolate. Okay, that's favorite. Okay, so energy, calorie, that you can do that. Okay, so the energy of the beam is in megajoule, and you can convert the chocolate will be 15 kilo of Swiss chocolate. Okay, you can. What it does, it revolves the proton to the close to the speed of light, and how many turns it makes. Also, you can 27 kilometer, and if you take the speed, so it is well understood. It's electronic theory, and we are pretty confident we do understood electronic very well. That is why we are sensing all these things in electronic theory. We are master. So it's not a difficult job to do actually, but we have to do very precisely. If accelerator is done, what happens to the detector? So do we have the detector technology? The detector technology is built by us actually as particle physicists. We are not accelerator physicists. We are particle physicists who do the data analysis, also build the detector. So this part is ours. Accelerator belongs to another head. It's called accelerator physics. We understood that, but we don't build it. Let's see just one. This is ATLAS is the biggest detector, is the heaviest detector. And you can see length is 140 feet and CMS is smaller but heavier than this. And this is very complex because it's not very straightforward detector. One detector has multiple detector, sub detector we say, and each electronic channel you have to understood actually it's working or not. This is a miracle because if you go to Switzerland, people don't miss to visit the detector and they may not see inside, at least they're happy to see what's happening. CMS detector is heavier than Eiffel Tower. You can think about now. Just to tell you how we detect, it's not just to detect. What we do actually, I showed you so many particles are produced, but all particles, most of the particles are short-lived particles. They will decay. We can only get the decay product, but there are few particles. Nature is beautiful. Nature always gives the clue. You have to find a clue. So nature gives few particles before it decays. You can still detect. There are handful of particles. One of them is electron. You know it doesn't decay. Proton, it's a long-lived particle. Neutron has lifetime. Before it decays, I can do that if it is moving very fast. Muon also lifetime is there. I can detect muon. Then two more particle, maybe pion and kaon. Other than other particle, before my detector decays. That means even Higgs is produced. End of the day, I will find pion, kaon, proton coming from Higgs. Now my job is to find whether this is coming from Higgs or top quark or bottom quark. There are many ways, many particles are there. But what I am finding actually, photon, proton, neutron, pion, kaon, that's it. My job is to find out whether this is coming from Higgs or not. That's also very challenging. So now what it does basically, let me just give you a glimpse actually how, I mean, it is very straightforward. My detector is divided into four more majorly. One is called tracking chamber. What is the tracking chamber? We know that it will just look for the charged particle. I will have a magnetic field. It will bend. From this, I can get the momentum of the particle. So I will have all the charged particle will give the track or signature in my tracking detector. And that will be bending. So that is good enough for me to know the momentum of the particle. So I know momentum of the particle. Then I also want to know energy of the particle, because momentum is not enough because mass is associated. So if you look at the classical field, classical physics, you'll say momentum and energy is conserved separately. In quantum world, there one is called four momentum conservation. Your momentum, mass, and energy is always linked together. So if I have three unknown, mass, momentum, energy, if I know two, third is known to me. So if I know the momentum, I still want to know the energy. Then I don't care of the mass. For energy, I have two detectors here just to measure energy. One is an electromagnetic calorimeter. That particle which interact through electromagnetically, that particle will stop there and lose all its energy, and I can measure. I know that particle which is photon and electron. So photon and electron will stop here. Nothing is going there usually. Then hadron calorimeter. Hadron means the particle which are made of quarks. Proton is a hadron, neutron is a hadron, pion is a hadron, it's a meson hadron. So that will be charged particle. You can get the momentum here. But this will penetrate through the calorimeter, but it will stop in hadron calorimeter. Then I get the energy of the particle here. If you look at the muon, it goes all the way, even crossing the last detector muon. Muon is a minimum ionizing particle. It has a penetration power, so it will penetrate all the detector. Any particle reach here, blindly I can tell that's a muon. That means I know it's muon. I know the momentum. I don't need the energy. I got it too. So this is how we have arranged in CMS and ATLAS. It's the same way we have done that. Once you have detector, you have to take the data. What are the data? When particle comes and interacts with your detector, it will create analog charge. Thus, now you need to know the electronics. How this analog charge will be stored in your detector as a signal. Signal process, everything comes into picture. That's called our data. So analog to digital, digital to optical, back to analog. This all conversion does. So you need to, electronics is most critical part we use. That is why the data is enormous. If what I said actually is a huge data we are collecting. And to do that, actually, we come up with a solution. It's called grid computing. Grid computing comes from the Large Hadron Collider. And we use for grid computing. After that, it's a industrial version is cloud computing. It comes from grid. Grid is whole world is connected. And we are handling the most data in the world. If you look at this is CERN. It's called TR0. When the data is collected, immediately the data is transferred to TR1 center. TR1 center is huge center which has the capacity to handle enormous amount of data, and that's limited to few countries. You can see most of the countries are developed countries. America has two. Then RAL is the UK has one here. Netherlands has one. INFN is Italy has one. So India does not have TR1 center. But TR2 center here, a lot of countries has, and India has two TR2 center, which we can connect to TR1 center and do the analysis in this. And we are also helping processing the data. Two centers are one in TIFR, another in VCC Calcutta. Okay, we hope we can get the TR1 center also. But that means we are also into the computing also. It does help. Then are you ready for the discovery? We got the detector ready, we got accelerator ready now. Data will come, we know the computing. Are we ready? Let's see. if I say I discover something, people will believe me or not? I have to have a credibility, right? I cannot come and tell you I have a beautiful machine, whatever it says. No, people are not going to take, right? So first thing is, before we do that, it is around 2010, when even we didn't get the Higgs discovery, people already started impatient. Where is Higgs? Because they thought Higgs will come definitely. Why? Because LS is a discovery machine, either Higgs or supersymmetry. So supersymmetry people are also excited at that time that supersymmetry may be discovered actually. So everybody was excited, and there was, if I remember when I was at CERN, before LSE start, we were discussing how to reject a theory. In the market, there is a thousands of theory because there is no experiment to verify, and theory can be given anytime. Until you reject, it's a theory. Now people are thinking how to reject this theory. Once data comes, rejection has to be done, no? So we can filter out who will survive. That was the most critical part actually. If you look at this actually, indirectly, if Higgs gives the mass, the most massive particle is Doppler, and here is W charge. So by looking at these two, they were thinking probably Higgs will be coming. It's indirectly, it's theoretically. But they were scratching their head actually. They cannot wait actually. They say, give us a data. Okay. So there is a lot of pressure on the experimentalist. If I remember when I was a CERN, there is a lot of BBC journalists come tell us what is inside, because they want to have news. So we were trained by BBC journalists how to talk to the journalist, because they will say CERN physicists say so. It's a big news. So you should be careful what you say to the. Interesting part is luminosity, which comes from the accelerator. Luminosity depends on the revolution frequency, number of bunch, how many bunch you are keeping, proton bunch, number of proton in a bunch. You should understand how many proton in a bunch. So number of protons per bunch is 10 to the power 11, not one proton. It's a bunch will be crushing, and from there you will have a one proton, not 10 to the 11 will go. So we make sure that one. Then area of the beam, when you bunch, when they cross, you have a special magnet to squeeze for a fraction of a second so that they can collide. After that, you release. You cannot keep the beam squeezed always, because there is a repulsive force. Proton will repel, and you are keeping 10 to the 11 proton together. Now, how much energy you need to keep them? It's very tough. So that is why. But for physics, for us, what is important is integrated luminosity, which is given by to us. Efficiency of the detector, that is us. We built our detector. We want our detector to be 100%. We cannot make 101%. No way. If you are very good, you can go to the 100%. There is a cross section. This is predicted by theory. That is where theory comes into picture. If their prediction is correct, my efficiency, I know this, I can get this. If this is correct, this theory is correct. And this number can be taken from any theory and see whether which theory is correct. That is where we make a handshaking between the experimentalist and theory. So once you know this, actually, I will also tell whole world that if we discover also, we'll tell you how to discover also, so that everybody in the world knows how to discover. And it is also accepted whole world. Then when you say, people should not say, okay, this is wrong, that wrong. No, everybody should accept. So how do you do that? This is a simple, in statistics also we need to know. So need to show that we have a signal that is inconsistent with the background. When you have collision, anything you do, you will have a signal and background. Yes or no? If you do the entrance exam, what you do? You want to select your signal, but you reject the background. You say it's a background. Otherwise, you can accept everybody. Yes or no? We have same thing. When collision happens, Higgs is my signal, while other particle is my background. So I have to say, if I see a signal, I have to say it is inconsistent. Means it's a signal. Number of observed, I can get it because I know the luminosity, how many observed I can figure out. Number of estimated background, that can come from theory, because theory can give you all the process, a background process, you take it, you know how many background will be there if your theory is very good. Okay, else you can get the from the data also. Now, need number of observed. No, nothing. No, it's but you have to connect actually. Yeah. Yeah, it's coming. So I can get the number of background, but that the fluctuation will go with the square root of number of background. That also I know. Then I can get the significance, which is this is given signal over square root of background. Then requires 5 sigma. If I calculate the 5 sigma, no. I will come back. So 5 sigma means that the probability that signal is a background is 10 to the minus 7. So that time whole world accept is a discovery. It is not 100%. Probably it cannot be 100%. But at this point, we say, okay. But initially, when I was a graduate student, it was 3 sigma. Then we realize sometimes we are wrong also. Then we go to 5 sigma. 5 sigma definitely we know actually, but still it can be wrong also. But we have to watch out. But when we say we have seen something, we have to reach 5 sigma. That is accepted whole worldwide. When we say 5 sigma, everybody accepts. And they know how you do this. This is known to everybody. Now we have a new machine, new accelerator. It has to have a credibility, right? So what do you do? And when you increase the luminosity, your signal should increase also. That means it's a signal. Otherwise, it's a fluctuation. So this calculation here has all the statistical, and we have also systematic comes from your detector. And that the detector physicist has to figure out. It's more complex, but we know how to handle. At this point, we're ready. And this is the Professor Peter Higgs visited ATLAS experiment, and used to we ask him to visit and see, we are going to look for your detector. So from UK, he used to come, and there are 2 detector, and he has to go to ATLAS as well as CMS. CMS in the France side, it is you have to drive. So sometimes it's easy, you get down in Geneva and ATLAS detector in Geneva. You just walk down, see, and go. Okay. So ATLAS or CMS are ready for the collision. You can see that is without inside the detector. Now, before we close down, we ask Peter Higgs to come, and he came and he visited one side and left. Then there was a kind of a joke that ATLAS discovered Higgs, because Higgs with ATLAS detector. Then he did not visit CMS, so CMS with Higgs was not there. So it's false alarm. Okay. So we make a lot of joke, and it's me who work in the pixel detector, and it's ATLAS detector. And this is the beam pipe. My detector is here. It's a fragile. It's a beam pipe goes here. Before we close, I also say bye bye to my detector. I cannot touch that detector because it's a radiation zone, and to go there also you cannot walk. It will be nice to see how world physicists work. They will be curling on the iron, and you can hurt your head. You have to wear helmet. Safety is first. Your shoe will be such a way that you cannot cut because it's iron, and you have to go like this. And sometimes you will feel like if somebody take a video and send to here, this worker goes there and works there, right? But that's the log we have for the detector. And this is what physicists are so happy to see. This is ATLAS control room. You see, November 23rd, that 2009, that first PP collision. First time accelerator made a collision, and we see our detector is alive. You see, we don't know how detector will work or not actually. Not all detector, because we are very curious that my pixel detector is sitting just too close to beam pipe. It can burn out easily. We turn off everything. We just only muon system and calorimeter who can sustain. We see just see that it's a fussing. That's good enough for us. Actually, it has life. So this is really a moment. If you this is here is fine. Only thing that does not allow to be okay. So once you start, we thought one proton should collide. You see, this is it's written timestamp also. We get 2009, 12, 11, 3, 38, sun time, run number, event number. You have already got two proton colliding. We want one proton to collide. And this is not even the 13 TeV. This is 500 GeV. That means when you squeeze 10 to the power 11 proton, you may get 10, 15, and we are worried about this also. The challenge is you have multiple event in one bunch crushing. That means you have to separate this event. Sometimes one time your detector is reading out, but it's not one event. Each collision is one event. So you have to separate that. Then you analyze. This is more challenging. That is where computing is most critical here. Algorithm. Now, how it looks like, one of the event. Again, 2012, see how it looks like. Do you see where the collision happens? Each line is a charge track and is a mess. Out of this, you analyze and you find Higgs. Okay. If you see this, you'll say, okay, throw this one. I don't think I can analyze anything. Everything looks same to me actually. Okay. Now it gets more complicated when you increase the luminosity and energy. So you have to deal with multiple event in one bunch clustering. You have to, yeah. Okay, you sit there again. So LSC data taking 2015-24. This is how I just want to say the summary that we have collected more than 215 inverse Prabhnavar, and it runs 24 hours, 7 days a week when we take the data. We have 8-hour shift, and shifters are physicists, not outsider. We cannot hire anybody. So if you're a graduate student, you will be trained to take the shift. Plus physicists like we also take. Also, we allow our graduate student to get trained. So this is one way to integrate them into the running condition. So in the control room, this shifter, all are physicists sitting and 8 hour. And no such problem happens because we have enough people traveling from many different countries. They take the responsibility when they have to be in the control room, and it's well coordinated. And so actually each year we have the data, we have a shutdown when you do the maintenance of the detector. There is a shutdowns. Okay, we're still continuing the data. The plan is to take the data until next year. then we'll stop it because the detector already damaged because of the radiation. Then we'll replace most of the detector with a new detector. Again, 2019, it will start. Again, it will run for 11 years. So plan is 2040, LSC will run. Okay. Now, when you have a new detector, new accelerator, people will say you give us a confidence that you know your known physics before you tell the discovery. So initially, our focus was to rediscover standard model. Everybody knows standard model. Now, standard model will be validated by CMS and ATLAS experiment at the 13 TeV energy. Energy has changed. You can redo the calculation and it should match. So first thing you see actually is very less 0.9 inverse peak carbon. We have seen phi. We know the particle exists. We see Jeff psi. Nobel Prize was given for Jeff psi. We see the Jeff psi. So we see known particles already. That means looks like physics makes sense actually, but that's not good enough. Then we go a bit more. This is where I personally like this because I always saw, because you see, when we saw first W, we know W boson exists. And standard model tells you if you are LSE energy, when you should see the W. If you don't see, something wrong with you. It is like a baby, 5 months, he should curl. If it doesn't curling, problem with the baby. So first 1 year for parents, like always problem, will go to doctor, okay, your baby is not holding this, some issue is there. You see, your baby should function. If you go to, in India, I didn't see, in US, usually you have a proper visit and they will expect your baby what to do. If they deviation, something with baby actually. This will be always traumatized. What will happen? My baby is functioning here. It's exactly same. Standard model tells you your detector should have this, accelerator should have this. If not, you have a problem actually. So this is like going through same kind of emotional that when we see, we will enjoy like anything. Yeah, we see. Then CMS, yeah, we also see. You see, this is critical for us. Now we have millions of W. I don't have excitement. But first W is excitement because with this much of data, you should see first W. And we see, we scan it and looks like. So you can see this kind of a milestone for you to validate that your physics is consistent with standard model. And then you can think of what I see, not consistent, standard model accept. Now we have to make standard model believe that we are seeing what you have told us. That is rediscovering standard model. Now, not only that, standard model on says, don't tell us one event. I have a number, cross-section, production cross-section. You do the measurement, compare with my number, and you see everything is matching with the standard model number. That is what makes everybody in the world to believe that standard model is rediscovered without Higgs. Now you go ahead and find Higgs and we'll believe you. That is where we are ready to go and find Higgs. This is excellent agreement with the standard model predictions. Important for background estimation for the Higgs boson. When we got the Higgs, these are the background actually. If I don't understand my background, I'll be in trouble. Now, just to give you a little bit about how Higgs will be produced in LSC. If I have 13 TeV energy, how Higgs will produce, standard model also tells you. If it is standard model Higgs, standard model Higgs tells you two gluon can come and fuse, make you Higgs. If this is the process, that is how your cross section will go as a function of mass of the Higgs, because standard model never told us what is the mass of Higgs. So we have mass from 100 GeV to 1 TeV. And you can find anywhere. If you find 300 GeV, you should match with this, then standard model Higgs. Otherwise, non-standard model. It could be Higgs, but non-standard model. You can find anything you want. If it is vector boson fusion, this is what it is. If it is associated G and W with Higgs, this is this. So this is already told by standard model. You don't have to worry about it. And if the mass, you just have to tell where did you find Higgs. And standard model tells you what should you see as a cross section. But mass is not given to us. So mass can be anywhere. Okay. Now this is the production process allowed in Large Hadron Collider. Anything else you see, standard model you say, it's not my Higgs. Okay. You can have different Higgs. That's why supersymmetry comes in the picture. Now, this is the production, but how Higgs will decay? Because I have to detect Higgs actually. How Higgs will decay? What are the decay product of Higgs? This is the decay. If you see at mass of the Higgs, and it can go to BB bar highest here. B quark, tau tau, gluon, CC bar, gamma, G gamma, G, everything is given. Standard model already told us. Now you find if it is not matching with the curve with the mass, then it's not standard model. So standard model is already clear about it, except mass. So you just have to find the mass of the Higgs. So now our job is, as experimentalist, you can tell us what to do. When you discover something, you have to be very clean. Why? No confusion is there. So if I look at all this decay mode, I find this is trouble. So B quark is a jet. W, it will have a neutrino decay. Gluon, jet. Tau will decay. CC bar, again jet. What gives me some kind of confidence is gamma, GG. Why? Gamma branching ratio is very small, you see, 10 to the minus 3 order. But gamma will have only one detector, electromagnetic calorimeter. I don't care all detector. I can throw all the detector. Only one detector. I don't have confusion. If I see there, I'm pretty sure. I have to be discover means I have to be very clear. Then GG is very small and the low mass. GG means 2G can go to 2 lepton. Muon is very clean. Only one detector. You don't have to worry about it. So there is no confusion. So when we discover, actually, we targeted 2 decay channel, though branching ratio is very small. Okay. If Higgs boson is 125 GeV, if out of 100.2% will decay to 240. You see, very less. That I need to have more data. But we decided to look for gamma and 4. Let's say 2 gamma. Just to give an example, 2 gluon comes, fuse and gives Higgs, and Higgs decays to 2 photon. Okay. And if it is 4 lepton, this is how it looks like. 0.2% is 2 photon, 0.014% is 4 lepton. All other I just throw because for the sake of a discovery, I don't want to touch because there is a lot of confusion. To convince people is very difficult. Then okay, you don't understand your jet, forget about it. So you tell us very clearly, there is no confusion. If you do that, it's a QQ bar going to 2 photon. I'll get 2 photon. These 2 photon, I have no way to understand which is 2 photon. But beautiful thing about the nature is when you combine 2 photon, if it is coming from here, it will show a exponential decay. No peak. But if it is coming to this, I will get always there is a place. So if I put signal and background together, I should see a excess here. So Higgs will be there, non-Higgs will be like this. So I can get the mass. This is one of the candidate. It could be this or this, I don't know. My calorimeter has a photon. Something, no track associated. You see, there is no charge track. Charge track means electron. So this is a candidate for Higgs decaying to 2 photon. Candidate, it could be background also. But we see some event like this. And you see actually in 2011, before discovery, we showed this plot in a conference. It says preliminary. Preliminary means if you take seriously, it's your risk actually. It's experiment has no business here. But to experiment, see some hint. You see, this is a hint actually. You see, there's some bump here. Slightly. People, theorists have already published paper discovery. We think this is Higgs because they want to be fast. Before we say, we didn't say it's a discovery. We just saw whatever, because it's not 5 sigma, no. Looking at this, people already decided where to Higgs. They are so curious about. Then both CMS ATLAS, see now, access same place. When you add data, it's 125. And this is what it shows actually. That means you are discovering Higgs in 2 photon, and we didn't have enough data. We use also 4 lepton channel to combine, because this is also clean. This is 4 lepton is the same problem, but you have a 4 leptons. You see, your signal will be your 2G 4 lepton. Background you can have here, here. This is background. This is background. This is signal. But the only good part is I have to deal with single detector. Electron, I can have electronic calorimeter. For muon, I have muon detector. I am not touching any other detector. So it's a good part. So you can see excess. 125, you see the excess. So 120. So you see 2 photon, 125, 4 lepton, 120. That means it looks like this is the same particle. And we can combine, and we see. Hello? कौन है? हैं? ना इसे कितना अच्छे हो जाए. So, sorry. This is 4 lepton signal, like 1, 2, 3, 4. Okay. This is one of the signal. Then 2012 and 2013 is the Nobel Prize. So Peter Higgs came to CERN. She was ATLAS spokesperson. Now she is the Director General of CERN, DG. And oh, yeah, but you want me to... You stay there actually. So that is where the Nobel Prize was given, saying that 125 is the Higgs. But just the mass is given actually. We have to check this particle's property also. Because once you know the mass, standard model tells all the characteristic of this particle. Now you have to measure all the characteristic of the particle and see if it is consistent with standard. What just seeing also, people are happy and celebration, because everybody gets a Nobel Prize and done. Then the difficult part for whom? Experimentalists to work hard. We are still working hard. Okay, people have taken luxury and waiting for. There is also TTH. We look for this production also, no problem. BB. So we find everything now. Coupling. Coupling is very important. What I said actually, it tells you if you know the Higgs mass, then all this particle will get the mass, and you can calculate the mass of the particle. This is the coupling, which is the standard. It's very nicely matching, you see. As if standard model knew how these particles were created at the beginning of Big Bang. What is the mass? So this is as beauty as this. You see, we have reduced the error bar like this. This is matching. How precisely? Okay. So standard model is very successful, giving everything. And now I'm showing a zoom up here. It is just within 5%. we are looking at 1% level sometime. If 1% fluctuation, new physics. But finding new physics is not sitting somewhere else. We have to find, it's very difficult to find new physics. Somewhere new physics is sitting, because in LSE, we did not find anything else new than Higgs. You should understand, whole world was watching that we'll get supersymmetry, extra diamonds, everything. But we have not found anything else except Higgs. And once we find Higgs, only the part standard model is happy, but standard model has a lot of things to explain. Standard model cannot be complete. That's very important. It does not explain neutrino mass. We know in Tamil Nadu we supposed to have neutrino observatory. That's the beauty of beyond standard model. So we were thinking to work for that. Pattern of fermion mass. Dark matter is still no answer. It just tells the visible matter. Visible matter is only 5% of this universe. 95% still dark matter, dark energy, which is standard matter, no answer. Baryon asymmetry, why antimatter does not exist in this universe? We don't know. Still standard matter has to find the answer. If new physics explain any of this, how do we get a handle on the relevant energy scale? This new physics, which will explain this, where do we find? Is it the energy of Large Hadron Collider will give us, or we have to go to higher energy, which we have to build a new accelerator? Nobody knows. It is a long way to go. Again, find something new. And here, theory has no clue. Again, experiment has to find a way now. Now, theorists have very limited way to say, because their theory has been rejected almost. I'll show you, people are scared that LSE may not able to tell us about our theory. Then you need a new machine. New machine does not come in 10 years also. It needs a lot of technological development also to get the higher energy. So this is a very tough situation for us together. How do we move forward? What do you do? Before, pre-Higgs, before Higgs, guaranteed discovery. Always theory tells you what to find, you discover. That is a guaranteed. That is always a reward. If you do the experiment, there is a reward actually. Beyond Fermi theory, we got W. Beyond bottom quark, top quark was discovered. Beyond electroweak, we got the Higgs. What do we do then? There is no theory to test beyond this actually. That is where we need to understand how do we get a handle on the new physics which will make this feasible. We have a normalizable consistent theory of strong and electroweak, but we have many unanswered questions. But now, if you have experiment also, no guaranteed discovery. Now you think about, if there is no guarantee for discovery, do you think you will spend $20–30 billion? There is no guarantee. That means we have to take the risk now. Guaranteed thing is over now. Now we have to take the risk and go. If we don't find, again we go. So this is our journey. That means you need a broad exploration. It's not a very pinpoint. You can be broad, open-minded discussion and how to find new physics actually. There is two ways. One is more luminosity. You take more data, do the measurement, go to the very precisely 2%, 3%, and standard model should be challenged. If you are the theory, we should find to the 0.1%. Any deviation, new physics. So this is one way, because you take more data. That is what LSE is going to do that. At this point, theory also improvement happens, because they also learn how to improve their theory. Because when experimenters tell you that, okay, now your error is big, they also work hard to reduce the error. And this is just like a back and forth between experimental theorists. Higher collision energy, which is challenging because you have to make a new accelerator, not the detector. That is also possible because you can reach the higher energy. So the high massive particle can be produced if it exists. Okay, this is one way to go. Many unsolved problem. What I said actually, you see so many theories actually, up to 1 TB, most of the theory is useless, thrown out. This doesn't exist. We are just saying exclusion. So we have reached 1 TeV, which within 1 TeV, you don't exist. Okay, then how long you will go? Up to we have 13 TeV. After that, done. They will say, oh, we need 100 TeV. Then okay, we have to go to new accelerator. That means another 30 years, 40 years of building the accelerator. It's not only 10 years. So think about. So this is the challenge for us to find new. And first, we look at the theory. Then we think we don't have to go theoretical way, because data is true and nature gives us. Rather than blind way thinking this theory is correct, can't we find on biased way, like rather than thinking a thing, you can see anything abnormal you see, throw at the theorist, saying, okay, I find something. Do you find? So this may be the thing to go later stage, because we don't have to say, we can go unbiased way, rather than saying, I want to test this theory. I'll say, it's my data. I look at either it's some excess, something, then we can make it right. This looks like in, then we can go. How do we do the stress test of the Higgs? Because once you know the Higgs, actually, it's very important. Why Higgs should be 125 GeV? Who made it actually? Higgs never made. Higgs theory doesn't say 125 GeV. We just find out. Now we say that who made 125 GeV? Who is the supreme power? And supreme power is sitting here. Where he is sitting, I don't know. We have to reach him. Who made 125? That is what the question. This is 100 TeV or 1000 TeV. Who is sitting above? Because somebody made 125 GeV, because Higgs mechanism did not make. There is no theory. We have to find super who is making this thing working, and that is called the new rich. And we don't know where he is sitting also. Okay, so we have to find this. Now, one more thing you can do. You can calculate this precisely. Now you have a computing power, saying that I can predict very precisely. You can test it. So that means experiment has to go smaller error bar to challenge. Okay, there is a room to do that. If you see any deviation, there is coupling of gamma, everything you calculate. If you see the deviation, it could be beyond some. It could be just saying that I don't know the nature of the physics, but I see something abnormal. So that is what we are going to do next 10 years also, doing precision measurement. That is why we have a plan for upgrade. Now Higgs sector is over. Now we have to go to upgrade. And in upgrade, what do we do? Yeah. So now we run here 2025. It will be shut down. Then we'll go to 2040 with the shutdown. That's the plan already. And we are trying to reach 3000 inverse femtometer of the data. And with this, what we can do, I show one thing that I showed you two collision. Now we expect 200 event in one collision. We have to separate 200 event in one bunch crossing. It's very challenging, but we have to be ready for that. With this is a prediction. It's not a calculation. If we have 300,000 units per point, where do we stand with the LHC, with the theory? Theory is the red color. The experimental error will be less than the theoretical error. So that means theory has to improve their prediction. And they have also 10 years to do actually, because we will not do. So they are also working hard. These are the parameters which is the basis of standard model. You can challenge those parameters experimentally. Now, the precision, what I said actually, this is 6 to gamma gamma. When we discover, you can measure this. We think we can go to 5%, and then you can check with the standard model. So every way we have to focus on the Higgs sector as well as the BSM excel beyond standard model part. Okay. In summary, I just want to mention that a large data set with precision measurement window to beyond standard model physics. So there is precision measurement. You can look at different production, new particle, and look if it is not consistent. It's a very open area and challenging for next 15 years. And this will be a basis for future experiment, which we are designing or proposing for linear collider, muon collider, everything comes. So we have a grand plan, what will go until end of this century. It's already planned what to do. Because the planning has to be done well in advance, but we have to find a hint which direction we go. Otherwise, again, we have to go way, which way we want to go actually. Maybe we'll go for the lepton collider, E plus E minus collider, which is very simple, and you can do the precision measurement, which will give you a clear view actually what the standard model is really the theory. And then if you don't find any deviation, you go to the explorer again, higher energy, which will be 100 TeV machine. That will go to be 100 kilometer of ring through France, Switzerland, all this country maybe, if it is in Europe. And that will be big investment also, but that will go end of the century also. So we are thinking. So what is the benefit of this actually? So what is the benefit? It's not physics actually. Physics we enjoy actually. Sometimes you enjoy when we come to talk to you. Otherwise, we enjoy every day. So what do we do for you then? If you look at this journey actually, most of the challenging technology has been made in this journey. If you go to the market, most of the high tech is coming from here. Your imaging comes from here, my detector. You go to MRI, that is developed by us actually, not by industry. Industry goes to you, you pay the money, you are happy. Who might ask them actually, where did you get this? They'll come back to us actually. Oh, they were making a detector, we thought it can be imaging, do it. So that is what the society gets from us, not directly, it's indirectly. Sometimes people don't know also how we contribute to the society, because it's indirect way, not the direct way. But I'll be happy to explain whatever. It's a beautiful field which gives you challenges. Physics is one thing, you will enjoy physics, but it also gives you technological challenge. If you're happy, take the challenge of technology. You open field actually, come and jump and do. We have opened lot of windows. Accelerator has to upgrade. We don't have technology yet. So we have to do R&D. We need more people to come and train and do the breakthrough. But it becomes more expensive now. So we have to convince everybody that this field is the way to go. And you might know World Wide Web also discovered or made in CERN actually, now IT revolution. So not only that, many things coming from here actually. Computing also you can see actually, we are in the forefront of computing. And then it goes to the application to the industry. So there is a connection that R&D happens. So good part of this actually, if you are good scientist doing R&D, you know that the product will be best. If an industry invest money, you will hire engineers actually. Engineer scientists to different level of competence actually. If a scientist does, by design, he will design a product. But engineer does for the work actually. So there is a big difference actually. You can make a product, but R&D, research and development, you cannot make in industry which will be open-ended. Every industry wants to have a product. Otherwise, it's a loss for them. They cannot run. This is not a money-generating machine. So R&D can only happen in the research lab or universities, where the physicist who is teaching the course, he has the time to do some research. And the product comes, then this goes to industry grade. So you have a mass who can do the R&D without paying too much. Whereas same thing, if you do in the industry, they have to take a big risk. If it fails, it's very disaster for that industry also. So what I said, this is very exciting field. You can see there is a technology, computing, electronics. Then you have sensors. What else you need actually? Mechanical. Then civil engineering is there. Then electronics is there. Electrical engineering there. Everything is here actually. It's a beautiful field actually. You may change your mind during the journey also. You have a way to change everything. And the beautiful part is, at the end of the day, you will be handling multi-terabyte of data, analyze the data, get your signal. If you know how to get the signal from this kind of process, you can be a best data analyst. And that best data analyst is prime for all the market in the world now. They want best data analyst who is trained, proven record. If you have proven record, everybody. So mostly in Europe, a lot of physics who does experimental physics, they go to industry also. And they are taken upfront, no question asked. And they're useful. So there is a way actually how we can make this field lucrative for our society, but it cannot be done for everybody. But it's a beautiful field. I enjoy it actually. So thank you.
Thank you very much. It was a wonderful lecture. It was an eye-opening lecture. No. So usually this is a memorial lecture, a Higgs memorial lecture. We used to have a 1 minute morning for scientists who passed away for memorial lecture. Higgs was passed away in April 8, and we conduct the lecture today. We want to know who is Higgs. So many of us don't know who is Higgs. What is his contribution? Now we have a good idea about Higgs. What is his contribution? Let us have a 1 minute silence of him. The reason passed away. Thank you. So now we'll jump into the question and answer session. Before that, now I have a couple of announcements. So many students want to have the certificate. So you can download the certificate if you are filling up the feedback forms. So feedback forms are available in Google. We provided the QR code and link. You fill up the feedback form and download the certificate. The second thing is we are doing a lot of things here in IIT. Professor is doing a lot of things. If many of you are interested to see his laboratory and see what is going on there and get something there, you can do that. You have to fill it up your option in the feedback form. Based on the options, we will be arranging we will discuss with the professor and find out a suitable day, and we will have a lab visit and we can interact with him directly. You can ask all the questions there. He has passionately explained 2 days in 2019 in his laboratory. We have more than 100 students who have come there, and we send them in batches because he is able to explain only 10, 15. His lab will have only 10, 15 students. We will divide the number of students into 10 batches, and we'll send it back. He is willing to spend time with the students to motivate them. And the third thing he was telling that now the scientific community is expecting more young scientists to voluntarily come forward to do science. And he says that now some people are opting for industry. Yes, industry is also having R&D. He is telling that now industry is having R&D. They are making huge investment on that. So if you don't get any returns, they will close it down. But if you are having a publicly funded research organization like universities and other things, obviously we will have a more progress in science. So any society which is progressing in science, it's going to be an advanced country. Because of that, you see the European countries and America, they become dominant because of they are advanced in science. We are still lagging behind science. because we are allotting very least fund for the development of science, and that too through public institutions. So please visit the laboratory and know about what he is doing and learn it. So let us go to another one announcement is there. As I explained to you that we are publishing 2 magazines. Today we are going to give you a complimentary copy of Tolir and Jantar Mantra. Please go through that. We'll be organizing a workshop on science rating soon. We'll get the announcement. Go through the magazines, and if you want, you can subscribe to the magazine. We can give the complimentary copy. Let us go to the question and answer session. We have one more mic. Yeah.
So, and audience feeling.
Yeah.
I wanted to know, like, why is the one? I understand that, like, when we accelerate the particles, we generate a lot of energy. But the thing is, like, is there any other way to generate the similar types of energy that we need for or like, because like we are thinking like we need to make bigger and bigger accelerators.
Yeah.
So like,
That is up to you actually. That question I put to the young generation. That's what we want actually. But if I don't have answer, then I expect answer from young generation. Okay. Yes.
I have a basic question.
Sure.
In higher school, like we study that charged particle produces field, electric field, and mass produces magnetic field. Sorry, the gravity. Mass produces gravity, and charges produce electric field. And if they are moving, they also produce magnetic. So, is it okay if I assume this Higgs particle is creating a Higgs field, or is it different?
No, that's typical. It's not very straightforward, and we don't see the field actually. You see electric field. What we observe actually, if you quantize the electric field, you get the photon. Photon is the quantization of the electric field. If you quantize gravitational field, you get a graviton. So if you want to see Higgs field, we cannot see Higgs field actually. So what we see, if you quantize Higgs field, Higgs would be there. So by observing Higgs, you are indirectly saying the Higgs field exists. We don't have direct manifestation of the Higgs field. So Higgs particle is the quantization of the Higgs field. When Higgs field was there in the beginning, if you go there, you should be able to find Higgs. And we find Higgs going to there. That is how it is being. And this helps you to interact this all the particles. The theory is all particles were massless in the beginning. Mass was not there. Then there was a Higgs field. And by interacting with the Higgs field, individual how they will interact the field, that is how they get the mass. So more massive means you have strongly interacting with the Higgs field. The top quark mass is 175. So that is a more strongly coupled to. Photon is not directly coupled, it's a massless. So we don't have a coupling with Higgs. If it's a Higgs decay actually, if your decay goes by a top quark, it's not directly because the photon is massless. So that means he never coupled directly to Higgs field. He through the top quark. This is how it is.
Then how Higgs itself is getting the mass?
This is if you have a mass field actually. Now it's not gravity. Gravity is not part of this standard model. So we detach gravity. So if you have a mass field actually, whatever field, if you quantize, then if you have a CF, if you condense, you get ice actually. Ice is just water actually. That's it. It's a condensation of the Higgs field actually.
So if other particles are interacting with Higgs field to gain mass, so the Higgs is also doing the same thing.
It is the what you see. If you quantize Higgs, that is why it doesn't tell you what the mass of Higgs. You see, this is the very fundamental question. I mean, from beginning, I'm saying Higgs mechanism has a drawback. It does not know how it getting mass of 100. So he said Higgs mass can be anything. I don't care. You see, Then the end, I said, now, who decides that Higgs mass should be 125 GeV? It is not Higgs field. This is an open question for us to find what you are asking. Who decides actually? Why not 100 GeV? Because who gives the mass 125 GeV actually? And we said somebody sitting above, which is controlling this field. Who is the above this Higgs mass? I said 1m. That m is physics, which is doing standard model stabilize. And where is the scale? Is it TV scale or 100 TV scale? I have no idea. Then Higgs mechanism doesn't tell you also. He never told us what the mass of Higgs. And how you tell who is controlling me actually? And you were asking exactly the same. That is an open question for us also.
What are the most likely theories to be beyond standard? Most likely.
To be honest, actually, I'm experimentalist. I don't have any fond of any theorist. Whoever comes for me, you fit, don't fit. I don't look at your face. Where do you come from? Are you coming from top university? I don't care. Okay. So I am very unbiased. At this point, none of the theory is fitting. Supersymmetry was when I was a graduate student. When I talked to a few people in Japan, they said, oh, he's working supersymmetry. Supersymmetry is the ultimate theory. So we thought they're the genius people. They know how math is. A supersymmetry is a beautiful math. And amazingly, it predicts. And we got to LSC. LSC supposed to, they were thinking, first discovery is supersymmetry, not Higgs. They don't worry about Higgs. They can explain Higgs also in their way. But we didn't find supersymmetry. Supersymmetry is dying. The people who have spent 20, 30 years to build a theory, and if that goes to the outside, then think about what will happen to other people. So we don't go with the theory. I said, a lot of theory is now rejected. We are going to, we said, okay, sometime it's not, I made a sometime joke. So I said, how many years left for you to be rejected?
Please correlate. Wait. Before going to the next question, the library people are waiting to honor the professor by giving a ponnadai. That's tradition.
Okay, I have to keep the side for
This is the library.
really good.
No, we don't bother about those things. We always talk. We are living in a society where we are doing this. You please correlate it's with the law of conservation of matter.
Higgs never tells. That is where reality is the truth is truth actually, and we have to. It could be bitter for us, but that's the truth. Yes.
Can I calibrate the energy in a let's
Calibrate. It's simple actually. Which energy you want? The energy of the the proton, which is, it's simple actually. I showed actually that when you revolve, you know the radius of curvature, you know the electric field, Maxwell's equation. It's very simple. Electromagnetic theory is most well understood at this point. Because of that, you have sensing, all this remote sensing. It's the electromagnetic theory. You know how to send a signal from you to the US, you know, talking to a friend. How accurately you can do? No, but the signal is transferred, no. So this is what it is actually. If you can do that, this is a simple thing actually. It just uses electric field. We know what the electric field do. What is the mass of proton? I know. Charge of a proton, I know. That's it. I can the acceleration. Then when I bend, I know the magnetic field. And I can tell you also when in the magnet will bend, it will reduce the photon. And
You can have the mic and I'll.
hello. Hello. So when it bend in the magnetic field, I also know accurately how much energy to lose also. So it is, you can calculate in your notebook also. It's well understood actually. Magnetic field, how it will bend, what is the synchrotron radiation, it's a mass dependent also. I know the proton mass. So how many protons are there in the bunch also, I know. Then you have to understand when you have a bunch of protons, how they behave actually. It's not single proton. Then you get to the 10 to the power 11. That is where we go to statistics, because I don't tell you exact number because it's roughly 10 to, you see, because 10 to the 11 proton I, but that could be some statistical error actually. That is always part of that. That will not affect you.
Sir, can we use the LHS data by
Yeah.
handling this?
You,
As a master student, can I use the data?
yes, we have take some data and put for outside student to get the feel. It's available. I can point you. You can take the data, do the analysis. There's so many people are taking because it is not easy to train everybody to motivate because things may not reach a lot of people. So we are giving some of the data to the high school student also. They can download. We give the program also how to do that. They get a feel. If they're excited, they go the direction also. We have. Okay. I can share the link also. Not whole data, but some, because you cannot download all this data. No.
Due to the high storage.
Yes.
Thank you.
Okay.
I could,
Yes.
from the lecture, I could see how.
You should introduce yourself. No.
I,
Yeah. Where are you from? Tell your friends here.
can I sit?
Yeah, yeah, you can see. Okay.
I'm Navin Kumar. I'm from Nobel department in IIT Madras.
Okay.
I'm a postgraduate in physics.
Okay.
It's a wonderful exercise. I could see how experimentalists work and how much computation work there's in the field. My question is like, if Higgs gives the mass to other particles, why treat differently? Different particles have different mass. What's so individual about these fundamental particles?
I said this is the coupling. Actually, I showed each particle how it coupled. He tells you also how they couple to the Higgs. That's how they get the mass, and that you can measure in the experimental
It's
also.
about Higgs or particles.
The particle coupling, how this will interact with the Higgs field. That's called coupling. Glue on. For example, you take the W boson. How W is interacting in Higgs field, that is a way it tells you how it is interacting. You can calculate that, and that tells you what should the mass of W. That's it.
So it's so individual about the particle.
Exactly. The photon does not interact, it's a massless. That's it. The photon is massless. It doesn't interact with Higgs field. It detached.
Yes. Before knowing this concept, like Higgs gives the mass to other particles. I visualize what I comprehend this mass and charge as like intrinsic properties. Textbooks schooling say that
Yes.
it's
Yes. Intrinsic properties. Correct. True.
Can I relate this mechanism to charge also? So why some particles have charge, some particles have not?
That comes from the quark now. If you the composite particle, you go to the
No,
quark.
Why some fundamental particles, even quarks, why boson?
Everybody has a charge actually. You can say charge zero actually. It's intrinsic property actually.
some bosons are no
Charge.
charge, but W bosons are charged.
Charge.
Um,
That is why the symmetry is broken actually. The symmetry,
Do
when
you,
you
do you think, I believe, there's another mechanism to explain charge also?
of course, the weak interaction will tell you everything actually. So three interaction is well understood. For quantum chromodynamics, for the strong interaction, electroweak, you can go to electromagnetic weak combine. It is well understood actually. You can do everything there actually. That's just standard model. Why it is a charge, no charge, everything is how the charge comes into picture also. You can evolve actually. That is what within the standard model is understood. Why neutrino has mass is not understood. Standard model says Newton should not have mass also. That coupling, but we have to see why it's mass. But photon has no mass is okay because photon is a gauge boson. The neutrino is a lepton. Neutrino is a lepton, yeah, and having very small mass. Still have to understand why. So this is challenging for the standard model also. Though standard model tells you most of the gauge boson getting the mass, the Higgs mechanism come into picture because of the gauge boson breaking the symmetry. Because photon gluon is massless, but the G boson is massive. Though it is also neutral gauge boson, neutral mediator particle, like a photon. But it's a photon, but mass is this. This is where the field was odd, and the theory was not able to explain because they thought all gauge bosons should be massless. That is why the broken. And because of that, Higgs mechanism come to explain that, and in turn, it explains everything related to the mass giving thing. Okay.
Basically, I think it comes because of E is equal to mc squared. Energy and mass are related. I
Same.
think at least there is no such relationship between charge and energy directly.
No.
So if it is there, I think such a thing also may come.
But yeah.
That's what intuitively at least it's.
But that is why we have different interaction in the scale. You see, strong interaction is independent of charge. You see, proton in the nucleus still is bound together.
Yeah.
So this is charge independent. So we look at the charge in the context of electromagnetic interaction. This charge plus minus can play only this. Other than that, no issue. Gravity doesn't care actually, charge. Gravity is mass actually. And strong is independent of charge also. If you turn off, that is why your isospin comes into picture, because if you turn off the charge for proton, there is no way to figure out which is a proton, which is neutron. You see, that isospin comes into picture to distinguish nucleons, right? If you study actually, okay. Yes.
Of mass,
Yeah.
I think it's slightly different from.
Charge. Yeah, yeah.
Keep your question sharp, because the library authorities are looking your time for 1 o'clock, after 1 o'clock. No problem.
So wonderful lecture.
Yeah.
My question might sound weird. How close are we to discover another new particle? See how Higgs did it 30 years before. How close are we to discover another new particle?
It can be next day, it can be next year, it can be next decade, because you are asking me as an astrologer as if I know. I have no roadmap for that actually. If I can tell you, then I will get Nobel Prize. I will be famous here itself actually.
I mean, there must be something which you might know.
No. I should not tell you I know actually, because I don't know. Nobody knows. If somebody tells you, he's lying to you. Don't believe.
Another follow-up on your sustainability. See, if we 30,000 tons of magnet, which is an LHC, what would happen to those magnets once the whole project is shut down?
Dismantle and recycle. We don't throw anywhere actually. We are responsible physicists actually. How?
How in the first place were they able to source that much magnet?
It takes 15 years. So it is, you see a place is beautiful, but if you go early, there is nothing actually. So we conceive from the ground zero. So if you look at some of the experiment, like next experiment, which I will be part of, like a linear collider, which may come to start after my retirement, actually. I may not be part of that, actually. The poor people like students who are sitting maybe in the kindergarten, he may come and run the experiment and he will say, who decided this thing actually? So I may not be there itself. He will say, so this experience is not easy to come actually. But if you're lucky, you will get from A to Z and you have a clear idea how it's very interesting to be part of that journey actually. It's challenging, but that makes you a perfect human being. The journey makes you a perfect. It's not the discovery actually. Discovery comes or not, I don't care actually. Because I'm not working for the discovery actually. If it comes, we say we find it. If it doesn't, I will tell you it doesn't come actually. I cannot lie. Just because the taxpayer in the world paid 20-30 billion dollars, I have to tell the lie, yeah, we find something. Because nobody is going to challenge us. That's not true. So we have to be honest actually. We don't find. We have to be honest. If we find, actually, we will get to the BBC all this news faster, not from me also. Because people are very clever to find actually what it. We found some excess around 600 GV, and people immediately publish like hundreds of paper. Next day, theorists are sitting, and within 24 hours, maybe which paper goes fast, they get accreditation. It's a time stamp is there also. There are people with the group sitting actually. How quickly team submit. Then we say this is not a, it's a fluctuation. Still we are watching. One of my students is also working in that channel. So, but we think if it is there, it's there actually. So if it is, it looks like another particle. But I said actually, it's not discovery. We see some excess. Some people push us like anything. If you say, you tell us no, then they publish the paper. And all of a sudden, the next day they say, okay, our theory is wrong. This is now, it's become trend actually. So for example, when I said 2011, we showed that we thought we will not show because people are so excited. Sometimes they tell you, they will put some word in your mouth also. They want, you tell this, that's it. Or you stand, I tell on behalf of you, it's done. So you have to be very careful. Then we said, no, actually, we are honest actually. Let people do the fight there themselves actually. Why should we wait for 5 sigma? We see something, by the time people think some of the group in the world, everybody in theory group who are, they celebrated actually. This is Higgs. Okay, we're done. Because they need excitement from us actually. There is no excitement for them. They're sitting quietly. When something comes, that is where the celebration starts. So we will have a challenging journey next 10 years with, we think we'll exclude most of the theory we are doing. Then there will be theoretical community will keep quiet and sitting, go to sleeping mode. Don't bother us actually. We'll say, don't bother us now. You are done with your theory. Go back and fix your theory. Then we'll have no disturbance. Then we'll say, okay, let's go to back to our data. Let's look at independence. Higgs is there. So we might need now AI, you see, because it is a jet. It's not, so jet means you may be able to understand what the jet formation happens also, because you are going to very different dimension. So those things will come when we can keep our theorist friend quiet. Because they say, we have been working, you are ignoring us. Okay, we are giving credit. Okay, no problem. Because later we need their help also to design, with a new experiment. No, they have to say yes, yes. So I think this next 10 years will be very challenging. So from my side, actually, when I was a postdoc, I discovered new particle also. So how do I discover? Because I never thought I would discover. So I was looking and I found, because I know the detector actually. So when I did that, actually, usually people who do the analysis, there is a photon, which is, you can get a lot of photons in the detector because electron moving can give you photon also. So they usually put a energy cut of 100 MeV. Above that, it's okay. Below, it's a lot of background. But to discover that particle, the new particle mass and the daughter particle mass, the difference is about 70 MeV. So difference 70 MeV, only photon can be decayed because the pion is 140, muon is 100. So there is no other particle. So that means if this particle decay, it will be radiative decay, giving a photon of 70 MeV. Now, 70 MeV goes below 100 MeV. So when I start the analysis, I put a cut above 100. That's why I'm throwing that. So nobody will discover. Then I said, okay, I will go 50 MeV. It's my decision. The 600 physicists working in Stanford, they are very genius people also. But they say, what the point actually? Why should I go there? Okay, we have so many physics we can do. They say, no, I go for 50. 50 means you have a huge background. Then I have to work on the background reduction. Then I should know the detector. Since I knew the detector during my PhD, so I reduced, then I see the signal. Then the data was not enough. I added like Higgs to gamma gamma with 4 lepton. I have 4 different channel I do. I got 5.1 sigma, which is discovery. When I say this thing, I was doing with one student actually, 2 people. It's very rare. Immediately collaboration said, you cannot be that genius, no. We're sitting here. Okay, you want to discover? Okay. They put immediately new team to scrutinize. And they have to do everything and you have to answer. They're your friend, but they will be sitting opposite to you. You defend us first. I had to go through everything and it was published and in PRL. So I was happy, but I'm not happy because I said 2 kids, no, somebody else has to tell me you are right. No, I told I'm right. So Bell experiment in Japan, they had more data, but they never look at because I was graduate student in Bell. When I discovered, they say, oh, it's possible. So they did after 1 year, they found and they reconfirmed. That is where I got relieved that it's not a false alarm.
What is that particle called?
Omega C prime. Right. That's my discovery, my name, everything. So you really have to tough because everybody will look at you as an enemy because you are going to get the credit for that. Okay. They are not going to give you credit just because you are a friend. No way. They are very honest. They will ask n number of questions so that they will be part of the paper. In the paper, 600 physicists will be there. And they don't want to be the paper until they understand actually. They say, no, I don't want to be the paper. So whenever there is a high profile goes, immediately another independent team has to be formed who includes the detector expert, physics expert, statistics expert, and they have to formulate the question. And you have to defend and verify. If you verify, your paper will be go, otherwise, no. And I was alone also. Nobody will help you because there's nobody, because you are going to get a credit. It is very tough, but it's okay because I defended, I told everything.
But now you are recognized as
Yeah.
you are recognized as the discoverer of that fact.
Yeah, everybody knows in the world actually.
Okay.
Yeah, there is one more question.
One more question?
Yeah.
If this discovery comes to people's world or protection, how the change is going to keep the people in a positive way? Or is it in the upper platform tier discussion only?
This discovery.
If we came to the protection, how it going to change?
Only a next session.
Okay, so this, let me tell you. So let's say you have a village. Okay, in a village, you have a priest who goes to temple. I don't know what he helps in the village actually. But everybody makes a namaste, pays the money, he is well respected. Why? He goes to the temple. Everybody goes to temple if you are Hindu, or if you are other, you go to masjid. There is a priest always. But they don't do anything to the society, if I see actually, but everybody respect. I don't know why. If you can.
They are placing truth without experiments. On which you have been dealing with so long.
No, okay. Just to tell you that it's not upper actually. Okay. In your family also, if you have uncle and father, grandfather, if your grandfather takes care of, let's say, outside work, you don't interfere. If something happens, he will tell you, but he will not report to you everyday thing because you are busy with your thing. It's exactly same. So for this field, for example, India is also part of. So we are working for Indian government on behalf of you also. I will not come every day and tell you will be bothered about because you'll say, I have any other thing to do or I will listen to your story. So when it comes something good, actually, that is where we'll tell you this is our responsibility to tell because you are paying the tax. And we are using taxpayers' money, means everybody's money. I have a responsibility to go back to you, not bother you. At least I have to tell you what is happening. If it is important thing happen, so you will say, okay, our people are doing something good. That is, if you are interested to know more, you have to come back to me. That means you are interested to know, not everybody. Then I can explain you how things moves actually, and you can also get benefited actually. So for this forum, for example, allows me to come and talk to you. Although I may not be able to talk to you actually. Okay. Yeah. Yeah. No, it's doing actually. If you come to my lab, we are making the detector part sending to CERN actually, Switzerland. In Chennai also, because at this point, I should not criticize or honestly say that people are not interested in science.
So I want to know actually what is
the thing is for LSE experiment, we have equal share. We also contribute intellectually, detector development everywhere because we have a share. So every country has a share because share means what? Let's say India has small community. US has a big community. So US has to pay more. Depends on how many physicists are competent to use this facility. So we pay our share also, and government of India is paying that through us. So we take the responsibility to detector development. We'll say this part of the detector will be made by India. The Indian government will pay for it. US will say this part. Then beautiful part is some part maybe cannot be accessible by India because there is an embargo. It's a dual technology, something is there. You can use for defense also. Because we don't work for any government because we are the fundamental science, we can access this technology and it can come to India also to my lab. Through this, we have technology transfer happens actually, which indirectly helps India also. Because if I know the technology, nobody will stop me to make in India actually. So the government get benefited through us to get the technology which is not accessible by government route actually. This is the beautiful way. And we also exchange. Sometimes we also give. So this is how we make the friendship. Like I should not go into this, but there is a war also. We don't care about war. We still as a friend. Even if Pakistan is part of that, we are friend also Pakistan. Pakistan is also part of the same experiment. So what we say actually, science is beyond politics. That is how we do, and we always protect our country's interest also at the same time as a responsible scientist also. Okay. But there are so many things happening actually. Okay.
Thank you. It's the time to wind up. Please give your feedback. The QR code for the feedback forms are available to the volunteers. You just scan the QR code and fill up the forms. I request Pitambar Sai Goyal will give the vote of thanks.
Many thanks, Professor. Professor Vijayan mentioned that physics lectures draw the biggest crowds. So it's easy to draw the crowds, but it's not easy to find professors brave enough to try to explain Higgs mechanism and the attendant experimental difficulties. Mr. Verma has just left. He wanted me to mention that in 2013, when Higgs was given the Nobel Prize, there were a lot of articles in the mainstream media indignant about how Bose never won the Nobel Prize. But it's true, Bose was rejected by famous scientist Oscar Klein.
Yeah.
But the other side of the story is that Professor Dirac, another greater scientist, fought for Bose and even got him introduced into the Royal Society. So I think that goodwill in science is what has enabled the collaboration with LHC, CMS, the tier 2 computational infrastructure that's here. And you know, that you can have different scales of goodwill. So in that regard, we'd also like to thank the library authorities for their goodwill in allowing us to do this. We're hoping to do this every 2 weeks. And I hope everyone will join us again for the next one. Thank you again.
Thank you.